Alright, let's finish up this problem from the last one. For part A, we got 2100. Okay. For part B, they're asking you to determine the prices for which quantity supplied is greater than the quantity demanded. So, we're basically just going to try to figure out where S of P is greater than D of P. So, 6P minus 900 is greater than negative 15P plus 2850. We solve it the exact same way. I'm going to subtract, or I'm sorry, I'm going to add 900 to both sides. This should be a 60. Add 15p to both sides. Divide by 75. So p greater than 50. Okay. So if the company charges more than $50 per phone, quantity supplied will exceed quantity demanded. In this case, the company will have excess phones in inventory. All right. Part C says graph both of these and labeled equilibrium price. So we're just going to graph these two equations. I trust you guys are all pretty good at graphing, so I'm just going to graph this one out. All right. So this is the supply, and this is the demand, and they intersect at 50, 2100, which is what these are the two values we found. Okay. I'm going to let you guys try this one. Pretty much the same thing, just different equations. All right. 3.2. In baseball, the on-base percentage for a team represents the percentage of time that the players safely reach base. The data given in the table represents the number of runs scored, Y, and the on-base percentage, X, for the teams in the National League during the 2006 baseball season. All right, here we go. First thing, draw a scatter diagram of the data treating on-base percentage as the independent variable. So basically, we're just going to take these values and put them in a graph. I will do that down here. Alright, when you graph it, it looks something kind of like this. Some of my dots are different sizes, but that's alright. Okay, use a graphing utility to draw a scatter diagram. You don't really have to. You could just use this one. I'll write down. Okay. Part C, describe what happens to runs scored as on-base percentage increases. Basically, we see from the scatter diagram that as the on-base percentage increases, the trend is that the number of run scores also increases. There is a positive correlation here. It's increasing. So I'll just write that down. As on-base percentage increases, runs scored also increases. Alright, I'll let you guys try this one over here. Okay. Alright, example 2. Determine whether the relation between the two variables is linear or nonlinear. So you're just going to look here and see if they have kind of a straight line here. For this one, as you can see, it kind of makes a straight line. It's not really curved, so this one is linear. This one's more like a parabola, so it's nonlinear. This one has a little squiggle in it, so it's nonlinear. This one's almost linear, but you can kind of tell that it is kind of exponential. So, nonlinear. Okay. You guys can try this one over here. Alright, example 3. Use the table in example 1 to select 2 points and find an equation of the line containing the points, and then graph the line on a scatter diagram obtained from the example. All right. Okay, so select 2 points. It really doesn't matter which 2 points you select. I'm just going to pick, let's see, from the chart, 32.7, 730, and 34.7, 865. Basically what I did was I used this chart up here. Remember, we're using the chart from example 1. I used this point and, gosh, where did I see the 730? Oh, this one down here. So I just picked those 2 points, and I'm going to find the rate of change, or the slope. Okay, so I've got m equals 865 minus 730 over 34.7 minus 32.7. And this will give me 135 over 2, which is 67.5. Okay? Alright, so I have my slope. I'm going to use point slope form for this. If you guys don't remember that, it's y minus y1 equals m times x minus x1. I have my m, and my x1, y1 was 32.7 and 730, so I'm going to plug those in. Oops. And there we go. Okay. Now, if I want to graph it, I'm actually going to convert this into slope-intercept form. So I'm going to distribute the 67.5. Let's pull out a calculator. Alright. 67.5 times 32.7. There we go. 0.25. Alright, then I'm going to add 730 to both sides. So I've got y equals 67.5x minus 1477.25. Alright, it'll be a little mini graph. Negative, we'll just make this 500, 1,000, 1,500. And it goes up very small amount. Close enough. There we go. Alright, I'll let you try this one. Okay, example 4. For this one, we do need to use a graphing utility, so let me pull one out. Okay, the first thing I did here, you need to turn your stat plot on. You click on here. What I just did there was I went to second, y equals. Here, hit enter. It will be on off already, but you need to click on. Click on this type. Then go to stat, go to edit, and type in your chart, the one from example 1, in L1 and L2. Then hit graph. I changed the window from 31 to 35, and then from 650 to 900 for the y's. And this is the scatter plot. Okay? Alright, graph the line of best fit on the scatter diagram obtained previously. Okay, so that's what we're going to do. Alright, if you go to stat, and you go to calc, you're going to go to linear regression, that's number 4. Then you're going to hit vars, go to y vars, function, and we're going to hit y1. So y equals ax plus b, this is your a, and this is your b. I'm going to go ahead and write that down. So y equals 49.19x minus 870.94. Okay. The slope of the line of best fit is 49.19, which means that for every 1% increase on the on-base percentage, run scores increase 49.19 on average. Okay. For part D, so that was part A, B, and C. For part D, letting x equal 34.1, I'm just going to plug that in. Y equals 49.19 times 34.1 minus 870.94. If you solve that, it's approximately 806 runs. Alright, I'll let you guys do the U-try. And that's all for 3.2.